Just 1 minute.
Okay.
And recording. So shall we start, Devaraj?
Yeah, sure. Yeah.
Okay. So I think there are not many participants. It doesn't matter. And so let me formally welcome Professor Devaraj on the Math Clinic platform. Professor Devaraj is PhD from IIT Bombay. And at present, he is in Indian Institute of Science Education and Research, Thiruvananthapuram. Before joining IISER Thiruvananthapuram, he has worked at Tata Infotech and Anna University. His areas of interest are harmonic analysis, sampling and reconstruction, and wavelet analysis. So today he is going to talk upon the topic non-orthogonal expansions in finite dimensional inner product spaces. So over to you, Devaraj.
Yeah. Okay. So good evening. Thank you, sir, for your introduction. Okay. So title of my talk is non-orthogonal expansions in finite dimensional inner product spaces. So this is my talk outline. That is what is beyond orthonormal basis, because orthonormal basis have been traditionally used for representing vectors or signals. And non-orthogonal, we mean we will have expansions in terms of what are called frames. And a special type of frames we discussed, that is what are called Parseval frames. And how we get Parseval frames as orthogonal projections of orthonormal bases. And a theorem related to that, that is Naimark's theorem, and one open problem we will discuss. So we use the following notations. N denotes an inner product space over the real numbers or over complex numbers, and this particular bracket denotes the inner product, and H dimension of H is N. This L2M denotes basically set of all finite sequences of either real or complex numbers, depends on the context. That is, you can think of as either CM or RM also. And by E1, E2, etc., En, we mean it's an orthonormal basis of the inner product space. And when our inner product space is either Rn or Cn, then E1, E2, etc., En basically denotes the standard orthonormal basis. Okay. So in finite dimensional spaces, by a basis, we mean a finite set of vectors that spans the space, that spans the Hilbert space or whatever finite dimension inner product space. That is, H is a linear, every vector in H is a linear combination of these elements. And if 0 is represented as a linear combination, then each must be 0. The sense that every vector has a unique representation as a linear combination of these vectors. So basically what you are talking about is you have basically a representation, that is a representation system we call it, that is every vector can be represented in the sense that every vector is identified as say C1, C2, etc., Cm. Okay. And this representation is basically unique. Okay. Okay, so again, finding these coefficients, that is C1, C2, etc., Cn, that is what we might mean by coefficients. That is, it is easy for finite dimensional spaces of smaller dimension. If you have a larger dimension, again, finding this becomes difficult. And if you are working with, say, orthonormal bases, then finding this becomes slightly easy. But the problem is, this gives you, though this represent, that is in terms, suppose if I know for a given vector, if it has a representation like this, say C1, E1, C2, E2, etc., Cm, Em, and if you have this C1, C2, etc., Cm, then we can reconstruct the corresponding vector using this particular representation, that is C1, E1, C2, E2, etc., Cm, Em. Now the problem is, suppose if you lose, essentially, in a typical communication system, and these two are not calculated at a same side. Maybe X is a vector that is available at one side. The other side, these values, C1, C2, etc., Cm are actually transmitted or communicated to the other end. And using this C1, C2, etc., Cm, this particular signal is actually, or signal or a vector is reconstructed at the receiving side. And what we basically want is the communication load should be as minimum as possible. That is, what do we mean by that? We need to have a representation wherein most of these coefficients are zero. That is what is called sparse representation. And resilient to erasers. Eraser meaning during this communication process, some values might be lost during the transmission. So if some values are lost, by that we mean that some coefficients are lost, and still we should be able to reconstruct without much significant errors. This is the background of this particular talk. Okay. Okay, that is what we have is, so you have any vector you have in the finite dimensional inner product space. It has a unique representation like this. So again, whatever I said earlier, so any vector or knowing this coefficient, you can reconstruct, but calculating this is difficult if you have a dimension is large. And if you are working with, say, an orthonormal basis, then this can be easily calculated. So you have a unique reconstruction, that is, F can be reconstructed using C1, E1, etc., Cm, Em. The problem is here, if few coefficients from this C case are lost, can one still reconstruct? Or is it possible to approximate F without much significant loss? Okay, this is a background. In this background only, I am discussing about what is called a non-orthogonal expansion. So what we have is, given an orthonormal basis, that gives you basically a representation system. That is system in the sense that every vector, there is an associated set of scalars, that is inner product F, Fi, I equal to 1 to n, where n is a dimension, you have basically n vectors. Okay. So that is, every vector has a unique decomposition. So what we are interested in is, okay, whether this decomposition is stable. Stable in the sense that there could be some kind of calculations errors possible here. Or if you are talking about in terms of transmissions, while transmission, this can be, there could be errors in this. Whether this is stable or in the sense that this kind of representation, whether it is stable. If it is stable, then reconstruction will be stable. That is, if either the measured value of error has F has an error, or this coefficient calculation has got an error, but still the reconstruction, we won't be losing much loss, or there may not be much significant loss in the reconstruction. That is what we want basically. So that is, even if there is a single error, that might cause significant loss in the reconstruction. Say, for instance, suppose I am working with, say, in 3 dimension. So I have, suppose I am working with the 3 dimension and I have a, say, a vector. So in 3-dimensional space, maybe it is sitting here and has got basically 3 components. Suppose one component is lost. Say, suppose this is my, say, Y, and this is my, say, X, and this is my Z axis. Suppose I lost one component here. It has got 3 components. One component is lost. Then when reconstructing, I'll be actually reconstructing this vector, its projection on the XY plane. So the deviation is basically this much. So this is a very much significant loss. So this is what we have been talking about. So we want to basically have a representation system which is resilient against the errors. So in order to do that, what we do is we introduce what are called redundancies. If you work with a basis or an orthonormal basis, there is no redundancies there. Again, without any redundancies, you cannot correct the errors or detect the errors, or you cannot have a mechanism which can reconstruct the signals without any loss, significant loss. So we need to have what is called redundancy should be introduced. Say, for instance, sometimes we don't want redundancies. For example, like if you have an image or something, you go for compression. Compression, because redundancies are there, you remove the redundancies by some mechanism, so we get a compression. Though as information they are different, but they are perceived as the same. But here the question is the opposite. That is, if you lose something during the transmission, there will be information loss in the reconstruction, but we don't want to have any significant information loss. So what we do is we introduce redundancy. At the same time, we need to have what is called a numerical stability. That is, you have a signal F or a vector F in inner product space, and we have basically the decompositions like this. And this is basically transmitted to the other side, the receiving side, and the receiving side basically reconstructed using maybe another set of functions. That is what is called a Fi tilde, and that should be closer enough to F. Even if there is a small deviation in these values, it should be closer to F. This is what we mean by numerical stability. And what we need is, in fact, something more. And we need to have this kind of, another set of vectors or same set of vectors, Fi tildes, which are in the sense that these coefficients must be sparse enough so that the transmitted information is very little, and still we should be able to recover back. If not for all the signals, at least for a class of vectors, we should be able to do it. And what we mean by that, this is basically what we call essentially the features of this particular vector. So where we may be working in several dimensions. Maybe my vector may be an object like an image, or it may be something, a signal, or whatever it is. Basically, we are looking at what are the significant features that actually determine the F. So this is connected with what is called deep learning, wherein we look for a certain a particular kind of representation that captures the features of this particular vector or a signal or whatever. Okay, so these considerations lead to what is called a non-orthogonal expansion, or what is called a frame expansion. So let me now give the definition of a frame. A finite set of elements in a Hilbert space or inner product space or a Hilbert space is called a frame for this space if there exist constants a and b such that this a times norm f square is less than or equal to sigma equal to 1 dm inner product fi square. This is less than or equal to b times norm f square. What it means is basically this decomposition is a stable decomposition. Okay, because given a vector f, it has a decomposition like this, and that decomposition is stable. Those numbers are called frame bounds, and of course, from this representation, this frame bounds are not unique, because if I have an a, I can again replace a by 2. Still, that is lower bound, and you can have b by 2 times b. Still, it will satisfy this. That means these bounds are not unique. So if you take infimum over all such upper bounds, that is what is called the upper frame bound, and supremum over all such a, it is called what is called optimal lower frame bound. So infimum over all upper frame bound is called optimal upper frame bound, and infimum is called optimum lower frame bound.
Devaraj, here you're norm as the L2 norm? Or
yeah, exactly. So this is square of the L2 norm. That the middle term is basically square of the L2 norm. The other one is basically the inner product. Okay, because it's inner product space, the inner product FF.
Okay.
Here it is the inner product in the whatever called inner product space, and here basically these are sequences in L2M. Little L2M, there's a set of all sequences, finite sequences of numbers, either real or complex numbers. This is a square of the little L2 norm, and this is a norm in the inner product space. Okay, let us look at some examples. So here, basically, the stability is achieved here because this is what a decomposition. This decomposition is stable. That is what it says. So it's within the control, even if small deviation, but deviation.
I have one.
Yeah. Any questions?
You want to?
Yes, sir. From this inequality, how can we conclude that or think this is the best reconstruction, or it will give the
reconstruction? Yeah, yes. Your question is how do I reconstruct, right? Yes, we will come to that one. Okay. Yes. Okay, we will come to that. Please wait for a while. Okay. Okay. Fine. Okay, let us look at some examples. Suppose you have a H is equal to, say, I'll take simply R2. And I'll take standard orthonormal basis vectors. E1 is 1, 0, 1, 0, again 1, sorry, 0, 1, 0, 1. So of course, this is not a basis, not an orthonormal basis also, because it's not, this collection is not a linearly independent collection. It's a linearly dependent set. Okay, so that is where I said redundancies are introduced here. And if you look at this inequality, the middle term is this one, sigma equal to 1 to 4, this L2 norm of this decomposition F5 square. This is FE1 square, inner product FE2 square. And you know, by either directly you can calculate or by Parseval's identity, this particular, the first two sums together, it is norm F square, and second two terms together, it is norm F square, 2 times norm F square. Therefore, it is a frame with the bounds A and B. Okay, A equal to 2 and B equal to 2. Similarly, I can look at if I take this E1, E2, etc., En, you have an orthonormal basis. Suppose if I remove one basis vector from this, then this is not a frame for H, because if you calculate this, the middle term, that frame inequality, sigma I equal to 1 to N, inner product F EI, that is norm square, this is less than or equal to norm F square, because I can add one more term here, that the missing term, that is inner product F E1, the modulus square. So I'll get this one. But you cannot find out a lower frame bound, because if I take F is equal to E1, then this particular, each of these terms will be 0. That means you cannot find out a lower frame bound condition. That means this is not a frame. So now we have an example of a frame, and we have an example of something which is not a frame. So as I said earlier, so supremum over all lower frame bound is called the optimal lower frame bound, and the infimum over all upper frame bound is called optimal upper frame bound. And if norm is 1, each of the frame vectors have norm 1, then we call the frame is normalized. So now it is possible that you can have an infinite number of elements in the frame collection, because say if I take 1 by n, I take V is equal to real line, and vectors are 1 by n. So if I take an inner product, it is something like a sequence 1 by n square. It is finite, so you'll get both lower and upper frame bound condition will get. But it is artificial, because normally we want to come from infinite dimensional spaces to finite dimensional spaces, not from finite dimensional spaces to some kind of infinite settings. So it is too artificial. So that is the reason we normally don't consider infinite number of vectors in a finite dimensional inner product space when you actually deal with the frames. And then there are little more terminologies before going to like expansion. So a frame F is called a tight frame if these A and B are equal. That is, you have something like this kind of inequality, that is sigma equal to 1 to m, F I square equal to A times norm F square. And we say a frame is a Parseval frame if it is a type frame with bound 1. That is, you have this equality, that is something like a Parseval's identity we have, that is sigma equal to 1 to m f fi square equal to norm f square. It's an equal norm frame if all the frame vectors have the same norm. So we will be discussing basically, mainly our focus is on having basically Parseval frames and the Parseval frames and then frame expansions. Okay, when you say frame is equiangular, that means the frame vectors, that is, if there is a constant c such that this angles are equal, absolute values of the angles are equal, then we say that the frame is an equiangular frame. And when a frame is called exact frame, if you remove one element from the frame, the remaining ceases to be a frame. There is no longer that collection will be a frame in frame. So you cannot remove even a single vector from the collection. So such a collection is called an exact frame. And basically these coefficients, this decomposition, these are called this inner product that f this thing. These are basically called what is called frame coefficients. Let us look at one or two more examples, then we will move on to the results. Suppose if I look at an orthonormal basis, it is always a frame, it is a Parseval frame because you have Parseval's identity. The frame inequality is basically the Parseval's identity. So it is always a frame, it is a Parseval frame. And if I introduce, I will take an orthonormal basis and then introduce, say, some zeros, just like that I just construct E1 0, E2 0, etc. 0 En. So then again, if I take look at the middle term in the frame inequality, then I'll get something like this. Okay, so I am getting again a Parseval frame. Okay, this is previous one. The third one, example third is an orthonormal basis and it is a Parseval frame. The second one is not an orthonormal basis, but it is a Parseval frame. And if I look at, say, if I repeat the vector, say E1, E1, E2, E2, etc., En, En, as in the first example. So this is sigma equal to 1 by 2n. Therefore, the middle term in the frame inequality, that will give you this one. That is again a type frame with the frame bounded 2. So like that, you can construct many more. So instead, if I take say E1 by root 2, E1 by root 2, again E2 by root 2, E2 by root 2, etc., En by root 2, En by root 2. Then again, it is a Parseval frame. It is not an orthonormal basis. It is not a basis because it is not linearly independent, but it is a Parseval frame. So I have an expansion like this. Okay. So similarly, we can construct many more. If I just add just one vector alone, if I repeat, say E1, E1, then the remaining all orthonormal basis vectors, that is E2, E3, etc., then again it is a frame, neither a Parseval frame nor a basis. But it is a frame with the frame bounds 1 and 2. But 2 we can easily get it by adding this term, and you can show that this is optimal because if one of the vectors taken to be either E1 or E2, then you will get this. Sorry, E1, then you will get this frame bound. And similarly, lower frame bound also it is easy to verify. So I'm not going to details of this because it is easy to calculate whether it is proving that it is optimal. We need to choose this F to be one of these EIs, then we will get the optimality. And if you look at this one, that is equally spaced vectors in R2, that is square root of 2 by 3, the vector 0, 1, square root of 2 by 3 into root 3 by 2 minus 1 by 2, square root of 2 by 3 into minus root 3 by 2 minus 1 by 2. This is again a frame. And this is equiangular because if you take the inner product of these vectors, angle between these vectors are same. That is Fi Fj is minus 1 by 3. That is easy to verify because it is minus root 3, that is root 3 by 2, root 3 by 2 by 3 into minus 1 by 2, it is minus 1 by 3. So, and you can easily verify that this because this will span is linearly basically independent. Sorry, 2 are linearly independent. So therefore, it spans R2, and we can actually see, we will see later any spanning set is frame in the case of finite dimensional spaces. So this is a frame. This is called an EQ. It is an equiangular frame because angle between them any two pair is the same. Okay. So now, suppose if I start with a finite family of vectors, then if the collection is an orthonormal basis, then this is a frame. and the converse is not true, because we have seen earlier, if I repeat the vectors in an orthonormal basis, that is a frame, but it is not a basis because it is not linearly independent. But in the case of finite dimensional, we are discussing finite dimensional. If Fi is a frame for H, if and only if it spans the space. So the span of Fi, that means any spanning set is a frame in the case of finite dimensional. This is not true for infinite dimensional, true only for finite dimensional. And if you have a Parseval frame with every vector is a unit norm, then it is an orthonormal basis. And in the case of finite dimension, that anyway we are working on finite dimension, an exact frame is a basis. Okay, so you cannot have a that is a minimal number which is spanning that one. That means it must be a basis. Okay, let us look at this. I mean, proof is simple. Okay, so let us look at some sketch of the proof. Suppose if I take a spanning set. Suppose, okay, let us take the case where this does not span. That means this span of Fi is not equal to H. Then I can choose something from its complement. That is, if I take F, which is a non-zero vector in the complement, then the middle term of this inequality, because then that will be perpendicular to each of these Fi's, and therefore this is 0. That means you don't get a lower frame bound condition. So that means the frame implies it has to span. And suppose on the other hand, suppose if you have something like you have a collection of vectors, finite collection of vectors that is spanning the space, then we can calculate this. This is easy to calculate because norm Fi square, you can use this the inequality, that is inner product Fi, that is less than or equal to norm of Fi square into norm of F square. You can collect all this together. So that is your B, that is upper frame bound. So upper frame bound is straightforward. For the lower frame bound condition, let us look at this as basically we want, this is what we want, this lower frame bound condition. We can look at this as a continuous function of F defined on actually H, your inner product space. But if I divide by norm F square on both sides of this inequality, I would get something like this. This is what I want. That is, I want this particular inequality I want. Okay, this inequality. So if I treat this as a continuous function defined on the unit ball of this H, then what you are saying is this on the unit ball, this continuous function must have a minimum. It should attain a minimum, and of course, this is basically this is a positive function. Because why is it positive function? If it is 0 for a non-zero F, that will violate the lower frame condition. So this is always strictly positive for F not equal to 0. Otherwise, it will violate the lower frame condition. Because you have a lower frame condition, this must be greater or equal to A times norm F square. Okay. Okay, what is the, okay, oh sorry, this is a span of this. Okay, so okay, we have a span is this one, but you have to show the lower frame condition. Okay, and suppose this is 0, then what does it mean? That means this inner product of Fj is 0 for every j. That means, so this F is perpendicular to the spanning set of V. That means F has to be equal to 0. Okay. So if this is, this inner product, this summation is 0, implies this has to be, F has to be equal to 0. If F is non-zero, this is strictly positive. Okay, because this Fi spans this H, so this cannot be 0. This is strictly positive for non-zero F. So by using the argument that this unit ball is compact because we are working on a finite dimensional space, this attains this minimum, and that A will serve the purpose of the lower bound. So that way, spanning set is a frame, the case of finite dimensional spaces. So now the next is basically you have a Parseval frame having unit vectors. If your vectors are unit vectors, then let us look at this. This is what we have, that is a frame frame equality, because you have Parseval frame. If these vectors are unit vectors, then if I instead of F, if I put Fi, sorry, F1, then what do I get? I'll get the F1 inner product F1 Fj square, and other side I'll have F1 square. I will split this into two, I equal to 1 dm, and then the first one. Because for unit norm, this is equal to 1, so you'll get basically you'll get this one. So you'll get this. You will get this. So this means what? Each one is 0. That means F1 is perpendicular to the Fj's, Fi's for I greater than or equal to 2. Similarly, we can show that for all others. So therefore, it is an already it is a spanning set. They are orthogonal and unit magnitude. Therefore, it is an orthonormal basis. Okay, so for the further analysis, so we need basically there are a set of operators. So by the way, any of you have any doubts in between, they can always interrupt me so that it will be a little more interactive. I think so far whatever I have discussed is very elementary, so I hope all of you are able to follow. Okay, so now let us start with a frame for the Hilbert space. Of course, we can define these operators even if this is not a frame. Okay, so we have what is called analysis operator. That is basically decomposing the function or a signal F into what we call it the components, or we call it frame coefficients. That is, it is a mapping. It maps H to little L2 of M. So every vector F, the corresponding decompositions. So this particular operator is called an analysis operator. And whatever frame inequality says that this particular mapping is a one-to-one mapping. It is a 1-1 map because the kernel must be 0. And this synthesis operator, basically from these components, we should be able to retrieve back the signal. That is synthesizing this F. This is basically adjoint of this particular operator, that is T star from little L2 M to H. This is given by it takes a sequence of finite sequence of values and then produces a vector, that is sigma I equal to 1 dm Ci Fi. Typically, these Ci's are these frame coefficients basically. So this is called a pre-frame operator or a synthesis operator. And we have the composite of two, that is T star. T star is basically, there is a small correction here. This is not T star, it is basically T star T. T star T.
Yeah, that's right.
T star T. So T star T is a mapping from H to H given by SF. That is when S of F is, when you composite of these two, this is sigma I equal to 1 dm Fi. And this is what is called a frame operator, this operator from H to H. And you can see that this is a non-negative operator. In fact, if I take S of F, then basically I'll get Fi, again inner product Fi F. That is nothing but the middle term of the frame inequality, that is sigma I equal to 1 dm inner product Fi mod square. So this operator is a non-negative operator. I don't prove all those properties. It is an invertible operator. It is a positive operator. It is again self-adjoint, that you can see from here. When you take adjoint of this is again T star T. It is a self-adjoint positive operator. And in fact, the optimal frame bounds are connected with the largest and the smallest eigenvalues of this particular operator. That each one is a result, so I don't go into that one. But it is a positive operator, you can easily see, because SFF is nothing but the middle term of the frame inequality. That again we have said it is bounded above and below by a positive constants. Okay, and in fact, this is again the inverse of this operator. S inverse of Fi is also a frame. This is called a canonical dual frame, and its frame operator is S inverse. Okay, this again I am not going to proof of this one. So what we have is S is invertible, positive, self-adjoint, and this the largest and the smallest eigenvalues are upper and lower frame bounds of this particular frame. And S inverse of this Fi is again a frame. It is called a canonical dual, and this corresponding the operator associated with that is S inverse. And if A and B are the frame bounds of F, then 1 by A B and 1 by B are all the frame bounds of the canonical dual. Okay, so we assume all this. So given those informations, let me write what is called, somebody has asked how do I get reconstruction. So the reconstruction is given by, this is a one such reconstruction. There are several ways of doing this. So F is equal to sigma I equal to 1 dm, say the frame with the frame operator, yes. Then F is equal to sigma I equal to 1 dm, F Fi, S inverse of Fi. You can, that given this decomposition, you can write this way. It's a one way of writing this. Equivalently, you can write it another way also. That means sigma I equal to 1 dm. This is F S inverse of Fi. That means these two can be interchanged, that can be swapped. That is Fi and S inverse of Fi can be swapped. Okay, still we will get the reconstruction. This is what the reconstruction which you get if you use a frame, but this is not the only way. Anyway, we will look at the a proof of this. Proof is because it is easy. If you have a SF, basically, this is what basically the frame operator is, sigma I equal to 1 dm Fi and Fi. So because it is invertible operator, if we multiply with the inverse, that is F is equal to sigma I equal to 1 dm Fi S inverse of Fi. This is the one of these expressions which I was shown earlier in the reconstruction. On the other hand, if I can write F is equal to S inverse of F. So S inverse of F is, you apply this again a new function F. You apply basically the frame operator is S acting on S inverse of F. S inverse of F is treated as a new vector. If I treat this as a new vector, then I'll get sigma I equal to 1 dm. That is S inverse of F, inner product Fi into Fi. So now again, this is right in the adjoint. This is F and adjoint of this Fi, because S is self-adjoint, inverse is also self-adjoint, and so on. So you'll get this particular reconstruction again. So this is with the canonical dual, we have a reconstruction, but this is not the only dual which will give you. Anything which is satisfy this property, we call a dual. That is, if you have a frame F and another frame is called a dual frame, if we get a reconstruction like this, that is sigma I equal to 1 dm Fi into Gi. Again, this dual is basically, if you have this relation, here also these two can be swapped. Fi Gi can be swapped. That is, you can have this kind of representations if you have a dual frame, and a dual frame is giving you a reconstruction. Another thing is what look at us. Okay, so I am working with basically a linearly dependent set. That is Fi frame, because we have introduced redundancies, so therefore it is a linearly dependent set. That means any vector I have multiple representations as linear combinations of these ones. Now the question is, for what choices of this AI, I would get minimum L2 norm. That is basically, if I choose a canonical dual, because I have a representation of F in terms of this canonical dual as for these frame coefficients as my coefficients. So that will give you the minimum L2 norm. That again, a proof I am not discussing, I'm just writing as a remark that requires some proof. Okay, so this AI square, that is any such representation of F in terms of this vectors, this will give you a minimum norm representations in terms of minimum L2 norm representation. And this dual representation is not unique. That is, if my frame is not a basis, actually it means what is called a Rees basis. Let us don't go into that one. So if it is not a basis, then I will have a infinitely many duals. That is, if I write Gi is equal to S inverse of Fi plus Hi, if Hi satisfies this relation, any such collection satisfying this is a dual frame. Not only that, any dual frame can be written in this form. So there are infinitely many duals. So the question is again, okay, that means that can be representations, you have many, not just one representation. But typically, we would be interested in what is a dual that will give you a sparse kind of representation. That is a much more difficult problem that we don't address here. At the same time, I may put a constraint. That is, basically, I don't want all the coefficients to be 0. Rather, I'll put a conditional, a cap on the upper bound. That is, the number of non-zero terms should be, say, some bound. I'll put L. Then can I find out such a thing? That is again much more difficult problem. Those are all connected with what is called compressive sensing and so on. I'll restrict, these are the number of coefficients, and I have a signal class wherein I restrict number of non-zero coefficients. So I should be able to find out representation, find out Fi and Gi such that every signal can be represented like this. So that are all connected with what are called compressive sensing or sparse representations. And they are again connected with something called deep learning, because those values, they represents basically the features of the F. Of course, in a very broad sense, it's connected to deep learning, but that is again a different area and a paradigm. Okay, because that it involves certain more also. There is something called a multi-layer and so on. Okay. Okay, so now what is the canonical dual of a Parseval frame? Because Parseval frame, what we have is, this is what relation we have. That is sigma I equal to 1 to n f inner product f I square is norm f square. So that means, but this is nothing but that is a middle term of this basically this frame inequality, that is nothing but s of f. So s of f is equal to f, and here again this is true for all f. This implies s is identity. So this is again a result, because it's a self-adjoint operator, and again I am working on it could be real or complex, but this is self-adjoint. So implies this is s is identity. So this is again a result. So not doesn't follow directly. Okay, so the canonical dual is itself. Because the canonical dual is itself, I have basically something similar to orthonormal expansion. That is, so in the orthonormal system, you have this expansion. F is equal to sigma 1 to m, that's f I. I have a similar expansion I have for Parseval frames also. Okay, so remember, Parseval frame need not be an orthonormal basis. So this expansion we normally get it in orthonormal basis, but here you get it even if it is a collection is not an orthonormal basis. If it is a Parseval frame, it gives you the expansion similar to that of the orthonormal basis. And similarly, our trace formula. So suppose you have a what is called an operator from H to H. The trace of this operator is with respect to usually any orthonormal basis, you write. Suppose EI is an orthonormal basis, then it is sigma I equal to 1 to m EI, and it is independent of the orthonormal basis you choose. Whatever is the orthonormal basis, that value remains the same. That is called a trace of the operator. So here, if I take the trace is okay defined as usual, it is suppose you have an orthonormal, the dimension is n, that orthonormal basis comes from n vectors. It is like this. Now I will what I do is I can write the reconstruction formula, that is this LEJ is my f. So if I use with using Parseval frame, if I write the reconstruction formula, I'll get this sigma I equal to 1 to m. This is my f, that is fj. That is what a reconstruction formula, like orthonormal expansion. Now by playing with this, so what you get is you just move this L to the other one, that is L star Fi, and then interchange the summations. So I will get so what do I get? I will just take out the sum and then interchange the sum. So I will get like this. That again I can bring it like this, because here again I have the reconstruction form. This is basically an orthonormal basis. Sigma j equal to 1 to n Fi Ej is Fi itself. So I'll get this. I can move it here again. The first component, that is Fi. So I have a what is called a trace formula. So this that is similar to orthonormal basis. It works for the trace also. That is, if we have a Parseval frame, the expansion is similar to orthonormal basis expansion, and trace formula is also similar to one you get with the orthonormal basis. Okay. So now if you have a basically projection, say suppose if you take a orthogonal projection of a frame, then we can show that actually it is a frame. I am not going to that one. Rather, I take suppose you take I have an orthonormal basis in a inner product space, say H, and if I take a subspace W, I take an orthogonal projection onto this W. So then this is again a Parseval frame. That is easy to look at. That is, if I take F in W, then it is a norm and its projection, they are the same. Therefore, F is equal to PF if I take F is in W, because it is in I am projecting this H onto W. So it is actually fixes the elements of W. Therefore, norm F square equal to norm PF square, and the PF is a vector in W. So it has got by Parseval's identity, this norm PF square is, it's a vector in H you can think of. So this is an orthonormal basis. So this is basically the Parseval's identity. So now I can, because it is a self-adjoint, so I can just, sorry, I'll take a adjoint and just move to other and self-adjoint. Therefore, it is FPI, PEI. So this is basically the middle terms in the frame inequality. So norm F square equal to this one. So therefore, this is a Parseval frame. So that is, if I have an orthonormal basis and if I have a subspace, if I take orthogonal projection of this orthonormal basis onto the subspace, then in this projected vectors, they form a Parseval frame. The question is, what about the converse? That is, I am given on a finite dimension inner product space, and I am given a Parseval frame. Can it be obtained as an orthogonal projection of an orthonormal basis sitting in a larger space? So that is what is called a Naimark's theorem. That is, yes, that is the case for finite dimensional. Infinite dimensional, some more condition is required. It's not exactly those, slight additional conditions you have to impose. That is, suppose if I have an orthonormal basis, if I have a Parseval frame on a space, say H, then it can be seen as, that is, if I have Fi is a Parseval frame for H, then there exists a larger Hilbert space, namely this one. H directs some, this n minus n denotes this dimension. There's another inner product space of dimension m minus n. The direct sum is again another inner product space where this Fi plus Gi is an orthonormal basis. That is basically the orthogonal projection of this Fi plus Gi is this Fi. That is, you have basically a frame with analysis operator T, and EI is a standard orthonormal basis of this little L2M, and P is an orthogonal projection from L2M to L2M. There is orthogonal projection onto the range of T, because the range of T is analysis operator. It maps H to little L2M. So it takes the range, and this is the orthogonal projection of this. In fact, for the statement, this is not required anyway. So then, Fi is a Parseval frame for H if and only if there exists a Gi in another inner product space of dimension m minus n, such that this Fi plus Gi is an orthonormal basis. That says that this
Devaraj.
Yeah.
What is capital N here?
Oh, capital N is a dimension of the inner product space H.
Oh, okay.
Okay, so capital N is the dimension of the inner product space H. Small m is a number of elements in this frame.
Okay.
Okay, and this m and that m are same. This little L2m and that m are same. Because you are mapping how many number of frame elements are, that many number of components will be there. That sequence. So this is a Parseval frame. Then we have okay. So this says that, okay, so any Parseval frame can be seen as an orthogonal projection of an orthonormal basis coming from a larger Hilbert space. Okay. So one way it is easy, because that anyway we have proved that the orthogonal projection of an orthonormal basis is a Parseval frame, so that we don't do it. But let us look at the other way around. That is, say 1 implies 2. Suppose if I have a Parseval frame for H, then let us define these vectors, because we have to somehow map what range of T perpendicular. That is, we take this Ci. Let us take EI is a standard orthonormal basis in L2 of M. That means it is 1 0 0 0, 0 1 0 0, etc. Those kind of basis vectors of L2M. Let us take Ci equal to EI minus PFI, and we will see that this Ci is basically in the range of T perpendicular. That is, so somehow we want a map. So we have basically, this is what our L2M.
Devaraj. Devaraj.
Yeah.
I think you can give a reference for the proof because
Yeah.
would like
Okay.
somebody to ask.
I'll give the reference. References are there. I have added that already there. Okay.
Because somebody may like to ask questions and it's about kind of.
Okay. Fine. Okay. So that way, anyway, the proof is there in the reference. I will give the reference. Not very difficult to see. Okay. So next, there is one open problem I will discuss. Okay, I'll take only 1 minute. Okay, this is what is called Schauner's conjecture. Okay, this conjecture is like a very old conjecture. That is what is known as the maximum number of vectors possible in equiangular type frame for Cn is n square. This result is known. This is the maximum number of vectors possible in an equiangular frame for Cn. The conjecture is for every n greater than or equal to 2, there is an equiangular frame for consisting of n square vectors in Cn, where this answer is known only for n equal to 2 to 15 and 19, 24, 35, and 48. Only these cases are known. Other cases are not known. Usually, the approach is take a discrete Heisenberg group of order n square, actually n cube, and then we normally consider this frame as irreducible unitary representations of those, and then you take orbits of that one. That's what the approach is, but still answer is not known. Okay, so these are the references. Whatever I have discussed, the proofs are there in this, mainly this Peter Casasa and Kutiniov, finite frames theory and applications, and the Christensen you may not find because that is mainly for Hilbert spaces. So one chapter is on finite dimensional spaces, and another one is for basically type frames by Waldron. So these are the references, and if you have any questions, I'll be very happy to take it.
Thank you, Devaraj.
Yeah, welcome.
In the meantime, for asking questions, please let me remind that Soumya has put the feedback form in the chat box. So please fill the feedback form. In the meantime, if you want to ask questions or any doubts or anything, you want to talk to Devaraj about today's talk, please unmute. We are only three of you, so you can unmute and ask questions. If you want to ask any doubts, clarifications. I think people are shy. Let me start asking you something.
Okay.
Anyway, it is very nice to see that even finite dimensional linear algebra can have applications. Normally, students ask, where do I going to use this kind of a thing? But linear algebra, we know that it has a lot of applications everywhere. It is another way of justifying the study of linear algebra, namely applications in actual reconstruction problems. And I think you've already mentioned that most of these ideas work in infinite dimensional Hilbert spaces also.
Yes. Okay. Some of the things will work, but certain things don't work.
Yeah, wherever finiteness comes, it won't work.
Yeah.
So let me ask you something which I don't know whether it makes sense or not.
Okay.
Supposing you have a frame with respect to which you are able to reconstruct, right?
Yeah, right.
Now, supposing your frame is, because of some reasons, your frame is slightly perturbed.
Yes. Not only perturbed, some coefficients can be lost also.
Yeah, let us say that they are not lost, but there is
okay. Yeah.
Fi is instead of Fi plus some
right.
something like that, epsilon I or something.
Yeah.
So when you reconstruct, you will get some other function probably.
Yeah, correct. Yeah.
So what is the relation between the perturbations of Fi's and the perturbed reconstruction? So is it sort of consistent or?
Yeah, so because here, so perturbed in the sense that, okay, the coefficients variation may be minimal. See, these vectors remain the same, that Fi, Gi, they do not change.
Right.
Because those are used for reconstruction. So they remain the same for reconstruction also. They are not perturbed. Only the coefficients are perturbed a little.
Right. So coefficients are perturbed. So
Yeah.
what effect has on the back
Yeah. Yeah, that is what the stability is there, because because it's a frame within that collection, that is the space, so the deviation will be minimal.
Okay.
Okay, that is because that is what a stability condition is. So the coefficients only changing, because otherwise F and the dual frame, the system where you have a communication system where sending set, receiving set, these are there. So only the coefficients are only moving around, there only the values are changing. So even if they are changed within the control.
Okay. Within
how many can be lost? That is again another problem. That is what is called erasure problem. Whether suppose one coefficient is lost, what is the optimal one? That is optimal dual pair. That will give you minimum error. That's another kind of problem. Okay, that is called erasure problem. That is, okay, suppose if I have a term is lost, what is a dual pair? That will give me an optimal reconciliation or a minimal error. Okay, so that is again another problem that also, of course, we are working on actually.
Okay. Anybody else has a remark or a question or doubt to ask? Devaraj? So if not, let me thank Devaraj coming over, sparing his time for the math clinic session and enlightening us about applications of linear algebra, I would call it, to some real world problems. Thank you very much. And before you leave, please fill the feedback form. 3 of you, Rajesh, Nair, and Mangala. Right. Thank you. Thank you.
Okay, thank you. Can I stop the sharing now? I'll stop the share now.
Yeah, please.
Okay.
And everybody take care.
Okay.
Right. Bye.
Okay, bye. So can I leave now?
Yeah, sure, please.
Okay.